What you're about to see is an unreleased moonfaker. Many of my Facebook friends and subscribers, they've been asking me for my thoughts on China's then upcoming unmanned Chang'e 3 mission to the moon. Now, at the time I thought it would be good to give my own little retrospective on how the on what happened during the Chinese space programs, all the way leading up to this point. And then after the Chang'e 3 had landed, or at least when China said it landed, I'd make the comparisons with Apollo and give my thoughts along those lines. This video was finished about a week before the Chang'e 3 liftoff, and while it was good to go, I ultimately decided to hold off on publishing it just yet, because while we can speculate about what may or may not happen, it's better to have actual data to work with. And of course, because the Chinese, they can't always be trusted. Right? They have shown to be deceptive in the past during their space programs, and so I didn't want to give NASA or the Chinese the heads up that I was watching them. I didn't want them to know that I was now focusing on Chang'e 3. That said, not only did I hold off on publishing this, I also made a very conscious effort not to talk about Chang'e 3 publicly, not online or on the phone or on email or whatever. Of course, after the Chang'e 3 landed, I was asked a few questions about that on radio, and now, finally, we have what I was particularly interested in was the geological data, and now that we have the geological data, I think now is the perfect time to share this. So, sit back, relax, and enjoy Moonfaker Chinese Road Trip. I have recently been asked for my thoughts on China's upcoming Chang'e 3 mission. The mission is to land an unmanned six-wheeled rover at the Yttrium. Among this payload is a television camera to beam back videos of the lunar surface in real time as it traverses the lunar surface, and a series of alpha particle backscatter and infrared spectrometers and diggers that will enable the rover to see the underlying structure of the moon's crust and make onboard chemical analysis of the soil. This leads to the big question: will Chang'e 3 prove or disprove the claims that man walked on the moon? This brings me back to my earlier video, Moonfaker Cold War II. In that video, I demonstrated that the Chinese would not have been likely to blow the whistle on NASA because doing so would be damaging to their free trade deals with the US government. And likewise, other space agencies, like the Japanese, Europeans, and even the Russians, have far too many joint projects underway with NASA. That video was made in 2008. Since then, a lot has changed, and yet stayed the same. Back then, the various non-Chinese space agencies were at NASA's mercy and needed them to lift their heaviest payloads into space. Now, with the cancellation of the Space Shuttle program, the tables have somewhat turned. NASA is now at the mercy of the Russians to get their astronauts into space, while the jobs of resupplying the International Space Station have gone to ESA, or private companies like SpaceX. And NASA is of course willing to pay these foreign agencies millions of dollars to get their astronauts and resupplies in orbit, and so the collaboration between these agencies is still going strong. Likewise, although the relationships between the US and Chinese governments have become shaky at best, the one thing that continues to keep them united is the free trade deals. But even so, as you will soon see, it seems that NASA has taken precautions. To this day, I am not sure just how much of the Chinese space exploration programs have been for real. I have always been suspicious of their first two manned space missions, for reasons already explained in my Cold War II video. And I am convinced that their first spacewalk was actually filmed in a swimming pool, a view shared by JPL engineer Dr. Q Zheng. It's truly a rarity when someone on the inside blows the whistle on a space claim. I asked Dr. Zheng for his thoughts on the Apollo missions, but he never returned my messages along those lines. I haven't paid much attention to the manned Chinese space missions since then, so I'm not going to conclude one way or another. As for their unmanned exploration of the moon, China so far claims to have sent two missions. Chang'e 1 orbited the moon between 2007 and 2009 before making a controlled impact in the lunar surface. The smallest object that its camera could see was 120 meters wide, meaning it had no way of resolving the artifacts. Interestingly, for a while it was believed by some that the first image transmitted from this satellite was actually a fake. They pointed out that this section of crater had been copied from Google Moon, and then badly jigsawed together. Various bloggers were quick to come down on this accusation like a ton of bricks. They said that this picture was actually a mosaic of 19 different image strips taken during different orbits, and that the anomaly was simply due to a slight misalignment of the two corresponding strips. With a slight adjustment, the anomaly is gone. I consulted with my credential proofreader along these lines. He was convinced that the Chinese photo was real, pointing out that the lighting between the Google image and the Chang'e 1 image were indeed similar, but not exact. So I'll just leave it at that. Chang'e 1, consider yourself lucky. Chang'e 2 orbited the moon between October 2010 and June 2011. This one carried a camera with 1 meter per pixel resolution, the same resolution as the lunar orbiter spacecrafts that resolved all 6 landing sites prior to the Apollo missions. The Chinese unveiled a full map of the moon comprising of photos taken by Chang'e 2. This article quotes Chief Scientist Yan Zheng of saying that the traces of the Apollo missions were spotted in these images. I assume he means soil plume disturbances, or rather, tricks of the light that he's probably mistaken for soil disturbances. But regardless of what he means, those images have never been published. To the best of my knowledge, only the Apollo 15 and 17 sites were resolved by Chang'e 2's camera, but the images released are zoomed so far out that you can't see any artifacts. In fact, this picture doesn't look much clearer than the Hubble image of the same location, and that was 100 meters per pixel. And before anyone wants to claim that these Hubble or Chang'e 2 pictures prove that Apollo 17 was real, I'd like to remind viewers that the Taurus litho was resolved down to 1 meter by the unmanned lunar orbiter probes prior to the Apollo missions. Some have claimed that the post-Apollo pictures of the moon show more detail than the pre-Apollo photos. Keep in mind that most lunar orbiter images that the public ever saw were photographed off TV screens, which in turn degraded the picture quality. But NASA, of course, had exclusive access to the unfiltered images. In recent years, the folks at the Lunar Orbiter Image Recovery Project managed to track down all the unfiltered tape reels and have been converting them to digital format. So far, they have published unfiltered lunar orbiter photos of the Apollo 12 and 14 sites, and resolution-wise, they look vastly superior to their LRO counterparts. As for Chang'e 3, the first question that comes to mind is, could this rover traverse to one of the Apollo sites and beam back close-up pictures of the artifacts? The answer is no. At Ceridim, the closest of the alleged Apollo sites is Apollo 15. In fact, the two sites are located at nearly opposite ends of this Mare region, some 1,000 kilometers apart. And the Chinese say that the furthest this rover will travel within its 3-month mission is 10 kilometers. By comparison, the Soviet Lunokhod 2 rover traveled some 30 or 40 kilometers across the surface. So if the Chinese rover cannot photograph the artifacts, then what about its ability to analyze the soil? I discussed already in my many videos on Apollo rocks that for a long time NASA had a huge stranglehold on lunar geology. The Apollo samples were either anorthositic or basaltic, and had a chemical, mineral and isotopic composition identical or near identical to terrestrial mafic igneous rocks and HED meteorites. Even before these rocks were distributed, NASA had published data from 3 surveyor missions showing the exact same thing. And since then, NASA has released remote sensing data from Clementine and Lunar Prospector suggesting that the Apollo geology was true for all locations on the moon. Was this data real? Or more likely, was it just fabricated data substituted to support NASA's fabricated rocks? Either way, with the release of this data, any claims that we only had a limited number of samples to fully understand the moon's geology was dismissed as a common misconception. Or as lunar geochemist Randy Korotev wrote on his site,
"As noted above, there are known exceptions to the generalizations, and we lunatics surely hope that we haven't discovered all the minerals and rock types that occur on the moon. However, known samples of unusual composition and mineralogy are rare, and usually occur only as small, less than 1 gram, clasts in breccias or in the soil. We have no reason to suspect, based on data obtained from orbit on the Clementine and Lunar Prospector missions, that any region of the moon is rich in types of rocks significantly different from those we know about or postulate might exist. Most ore-forming processes on Earth involve water, so we would not expect any hidden ore deposits on the moon. Keep in mind that if more than 40 lunar meteorites have been blasted off the moon and found on Earth, then at any given point on the lunar surface, there can be rocks from any other point. For this reason, the fact that the lunar surface was poorly sampled by the Apollo and Luna missions is in itself not a good reason to suspect that rocks vastly different from those we have studied exist at unsampled points on the moon. Tens of thousands of lunar rocks and rocklets have been studied since the Apollo missions. It is highly unlikely that any yet unfound lunar meteorite will differ substantially in the minerals it contains or in its geochemical character from the Apollo lunar rocks.
That was written around 2001. In 2006, the Smart 1 crashed into the near side of the moon and sent lunar material into space for scientists to analyze with ground-based equipment. The ABC reported that this material was different to those that the Apollo astronauts supposedly returned.
It's almost 500,000 kilometres from the moon, but this radio telescope is also very close to the action. 3 years ago, the European Space Agency launched the Smart 1 space probe. Today, it was on a collision course for the moon.
All the other controlled impacts on the moon have generally been either on the far side of the moon where we couldn't see it, or in the polar regions where it wasn't so easy. This is the first time we've had the opportunity to really get a good glimpse of it with all the telescopes that are available.
Observatories in Chile and Narrabri in New South Wales also were trained on the probe. But at 26 metres across, the Mount Pleasant Observatory outside Hobart had the most sensitive equipment to help determine what the moon is made of. Finally, collision time. By punching a 10-metre hole in the moon's surface, the probe has uncovered minerals different to the rocks gathered on the surface during moonwalks. The key is the chemical signatures in the dust and debris thrown up by the collision.
And also the radiation in the infrared can tell us the temperature, which tells us how much energy was released and what the material must be made of.
Today's collision could also unlock the secrets of the moon's origins.
So each theory of moon's formation has a prediction for what the moon should be made out of, and by looking at what the moon is actually made of, we can eliminate some theories and reinforce others.
It's hoped results will be available within a year. Michael Lockerbie, ABC News, Hobart.
After I pointed this out, that misconception about the moon being poorly sampled suddenly became law. One propagandist went so far as to say that finding different minerals was to be expected, and that's despite, in his previous videos, his blatant and in some cases shoddy plagiarism of everything else Randy Korotov said. Phil Plait once claimed in a radio show that the samples returned by the Soviet unmanned missions were chemically identical to their American counterparts.
The Russians did bring back, they had a sample return mission, I think it was Zond 5. It was one of their missions that went to the moon and brought back, it was like 100 grams. It was a very, very small sample because it's hard to bring back a lot. And, chemically and all of that, they were identical to, or at least, close enough to what was found on the moon.
Not only did this claim turn out to be false, but I was used as a scapegoat for it, because I happened to paraphrase what Plait said in my response to him. By far the biggest difference between the American and Soviet samples is that the former contains ferric iron, while the latter samples do not.
There is a linear relationship between the average iron content and the absorption coefficient of a strong polarized crystal field band at 1,250 nanometers in the Luna 29 plagioclase, a soil that is not reportedly oxidized or hydrated. However, the iron values of plagioclase crystals from the altered Apollo 15 and 16 samples fall off this line, a factor that may be related to the presence of significant proportions of ferric iron.
Of all the Apollo samples to contain rust, the Apollo 16 samples in particular were notorious for this. Geologists Hunter and Taylor, for example, analysed 148 different rocks from Apollo 16. 32 of them contained trace amounts of rust, 30 had ferric iron present, and another 20 contained abundant ferric iron. The samples with abundant rust included 61016, better known as Big Muley, the largest rock ever allegedly returned from the moon. It is important to note that ferric iron is the 3+ oxidation state for iron, and is created by exposing the iron to an oxygen and water-rich atmosphere for a long time. Additionally, the Apollo samples contain water ranging from 1,000 to 6,000 parts per million. This falls perfectly within the range for terrestrial rocks, And contrary to what some have suggested, the deuterium-hydrogen ratio of this water is also consistent with the terrestrial range. By comparison, the only Soviet samples to contain water was the Lunar 24 sample. It contained 1,000 parts per million and was found only by drilling 1.4 meters under the surface. Yet NASA was able to find up to 6,000 parts per million in surface material. Is it any wonder why this Russian paper was published in the 1970s but ignored in the West until last year? Additionally, the only places where the recent remote detection missions have found comparable amounts of water on the moon is in the polar regions. As you can see from this Chandrayaan-1 data, that signature of water is nowhere to be found in the equatorial regions. It should also be pointed out that the strongest readings turned out to be 3,000 parts per million at the North Pole, only half of the highest water contents in the Apollo rocks. So now we come to Chang'e 3. As I said before, despite their trade deals still going strong, the relationship between China and the US has become rather strained, so it is unclear whether or not the Chinese will go along with NASA's lies about lunar geology. If the Chang'e 3 soil analysis is going to be factual, I foresee reports about rocks containing minerals different to the Apollo samples, no water unless you drill deep for it, and absolutely not one trace of ferric iron. And it seems that NASA and their friends at the Arizona State University have prepared themselves for the worst. In this October 15, 2010 article on the LROC website, we find this statement. Currently, the Chinese lander is slated to land in the Siniceridum sometime before 2013. Why Siniceridum? The wide-angle camera topography map shows this area to be relatively flat and nearly featureless. However, as the LROC narrow-angle camera keeps showing us, there are no featureless spots on the moon. Everywhere on the moon is fascinating. Siniceridum is a Maria-field impact crater that superposes on the Imbrium Basin. It is far from any of the Apollo landing sites, with the closest Apollo 15 being more than 1,000 kilometers distant. Scientists would love to have a look at the chemistry of these basalts. How much do they differ from the Apollo 15 basalts, which are formed on the other side of the Imbrium? Again, this was written after the Smart 1 impact, which itself occurred after it was previously said that finding different rocks at unsampled sites was a common misconception. A common misconception that has now conveniently become law, now that NASA has decided to cover their tracks. Well, now the Chinese say they've landed, and now we have the geological results! Right off the bat, I have to say though that the Chinese have been very cagey about the data that they've released. Most of the photographs released to the public were photographed off the screens in the Beijing control room, and very little technical data has been published. The photographs have, however, proved to be quite interesting to compare with the Apollo photographs. I spent a good time discussing them on a recent Reynolds Reveal radio show and could easily make 10 or so videos on these photographs. But quite frankly, I think the photographs pale in comparison to the geological data.
The Chang'e 3 lunar probe has successfully conducted scientific analysis of the moon's soil below the surface. It was done over a period of 2 months. Scientists say the job is very challenging in that they need to control a robotic arm 380,000 kilometers away, and this requires a millimeter-level precision. The lunar rover called Yutu found there are 11 chemical elements existing in the soil, including magnesium, aluminum, and titanium, and iron, and all useful resources that can potentially be used.
The Chinese Academy of Sciences website carried this article about the results. An initial analysis indicates that 8 major rock-forming elements, magnesium, aluminium, silicon, potassium, calcium, titanium, chromium, and iron, and at least 3 minor elements, strontium, yttrium, and zirconium, of the moon can be identified in this spectrum. This is quite interesting. While all 8 of these elements are indeed found in the Apollo rock samples, what caught my attention was China's declaration that one of the 8 major elements found at the Chang'e 3 site is chromium. This is a huge anomaly. In igneous rocks from Earth, the Apollo samples, and also the HED group of meteorites, chromium is either a minor element or a trace element. It ranges in value from between 200 parts per million to 2,000 parts per million, or 0.02% to 0.2% by weight. The highest quantities of chromium that I'm aware of are some terrestrial ultramafic rocks, which can contain up to 3,000 milligrams per kilogram of chromium, which is 0.3% by weight. To be a major element, the element must account for more than 1% of the rock's composition. Likewise, to be a minor element, the element needs to account for something between 0.1 to 1% of the rock's composition. Yet the Apollo sample compositions of strontium, yttrium, and zirconium all fall below this range, meaning that they are trace elements. Not only is this a significant mismatch between the Apollo samples and the Chang'e 3 site, this is well outside our database. I am aware of no such rock type, terrestrial or otherwise, that contains chromium as a major element and strontium, yttrium, and zirconium as minor elements. Now, to be fair, there are some rare mafic and ultramafic igneous rocks on Earth called chromatites, which are 90% composed of the mineral chromite. As such, these things can be over 50% chromium oxide by weight. But they also contain titanium and calcium as minor or trace elements, not major elements. And their strontium, yttrium, and zirconium are all in trace amounts. Of course, this passing mention doesn't really tell us much regarding the exact quantities of these elements found within the soil. To find that out, we need to extract that information from the X-ray spectral data. Without getting into too much detail, this device basically works by using a radioactive source to shower the rock samples with a spray of X-ray photons. By doing so, the radiation interacts with the atoms that the rock is composed of, and subsequently, the said atoms release energy, which is then measured by the instrument. The amount of energy plotted on the horizontal axis helps you narrow down just what type of element the atom must be, and the counts plotted on the vertical tells you how much of the material there is. Finding the weight percentages of these elements then becomes a matter of simple math. First of all, the peaks labelled as iron 55 and cadmium 109 are simply noise from the radioactive source that the instrument used, so we can ignore them. They are not part of the moon's composition. We can also ignore these peaks labelled collimator copper and collimator nickel, since they come from an interaction of the X-rays with parts of the spectrometer itself. And secondly, some of the elements are labelled with Ka or Kb, A meaning alpha and B meaning beta. This simply refers to how the scattered radiation interacted with the electron shells of the elements. So for the elements with two separate peaks, we can add them together to get the total counts of the element. After measuring the heights of each peak and then converting them from log to linear, I arrived at the following counts. Right off the bat, the counts for the iron 55 noise are shown here because I needed them to try and isolate the peak for iron K-alpha. As you can see, the peak for it seems to be overlapping with the noise from the radioactive iron 55, so I needed to make some calculations to separate them. Looking at these counts, the alpha-beta ratios seem to be quite similar, with 6.9 for calcium and 6.2 for titanium. So the average ratio between alpha and beta is 6.53. If we divide the iron 55 K-alpha noise by this ratio, we get 2089 for iron 55 K-beta noise. Therefore, the plain old iron K-alpha is 9081. This is an alpha-beta ratio of 5.2. Close enough. Now that we've got our counts, we need to convert these to weight percentages, and we do that by multiplying each group of counts by the atomic mass of their respective element. I added all those results up, and then calculated the percentages of each element. That all looks pretty good. But wait, something appears to be missing. There's no oxygen listed in these elements. Both Earth rocks and meteorites contain abundant amounts of oxygen, around 40%, in the form of oxides. So why are we not seeing that here? The problem appears to be that oxygen has a spectral peak outside the range of this detector. In X-ray fluorescence, oxygen has a spectral line of 0.525 kilo-electron-volts. But this chart suddenly drops for anything below 1 kilo-electron-volt. That means anything below sodium or magnesium on this table won't be picked up. That includes oxygen. No matter though, we can add it in. Assuming that all major elements are in their common oxide forms, we can simply determine the oxygen count based on the molecular form of each oxide. For iron, I will use ferrous oxide rather than the ferric oxide form, since we don't expect to find any rust on the moon. So by adding the oxygen count on, and adjusting for its atomic weight of 16, we can determine a new adjusted count. mostly in terms of chemical compounds, and we can calculate new percentages to go with them. Now that we have our weight percentages for the Chang'e 3 site, I decided to pitch them against those for the Apollo soils and see how they compare. Just for the record, for the major elements of soils from all 6 missions, I cited this paper by Basu and Riegsecker printed in the workshop of the New Views of the Moon. As for the trace elements, for Apollos 11 and 12, I used the numbers printed on page 118 of Mason and Melson's book, and for all the other sites, I used the PDFs on the Lunar Sample Compendium website, which I selected at random. The numbers need to be seen to be believed. For starters, the magnesium content in the Apollo soil and rocks ranges from between 5 to 11%, but at the Chang'e 3 site, it is only about 0.2%. Aluminium is generally about 15% by weight in the Apollo rocks, an exception being Apollo 16, with an enormous boost in this metal. But again, the Chang'e 3 soil is not even comparable and doesn't even account for 1%. The Apollo rocks are predominantly silicon dioxide, with a weight percentage generally around 45%. Chang'e 3's silicon is reduced by a factor of 11. There was a correlation between the potassium contents of the Apollo and Chang'e 3 soils, with the latter containing more potassium than Apollo 12, but less than Apollo 14. So nothing out of place here. But don't get too excited just yet. Remember what I said about the Apollo soils being predominantly silicon? Well, by any definition, it appears that the Chang'e 3 soil is predominantly calcium-based rocks, with about 43% calcium oxide, nearly 4 times the calcium concentrations in Apollo rocks. The second most abundant element found at the Chang'e 3 site appears to be titanium. The Apollo soils are all generally low in titanium, with slightly less or slightly more than 1%, an exception being the Apollo 11 samples, which were well known for their high titanium contents. But again, the Chang'e 3 soil contains about 5 times as much. It seems my hunch about the chromium was right. It is nearly 2 times greater than 1%, making it a major element. And as we discussed before, in the Apollo soils it is a minor element. Their chromium is reduced by a factor of about 4. Finally, the iron quantities of the Chang'e 3 site was about the same as that found in the Apollo 14 rocks, and together they fall right in the middle of the iron range for Apollo rocks. So overall, nothing anomalous here. Unless of course you consider the fact that in the case of Apollo rocks, their iron is partially or significantly rusted into ferric oxide, which would affect these columns noticeably. Unfortunately, because of their blind trust with NASA, most geologists erroneously dismiss this ferric oxide as a terrestrial contaminant, rather than recognizing it as evidence for a hoax. And so often when you see ferrous oxide percentages listed in studies on Apollo rocks, chances are that the iron has been recalculated into the ferrous oxide state. That covers the major elements. As for the minor elements, it seems that my hunch was again right. In the Chang'e 3 soil, strontium, yttrium, and zirconium all account for more than 1 to 0.3% by weight, which puts them nicely in the minor element range. But in all of the Apollo soils, these minor elements struggle to make more than a few hundredths of 1% by weight. In some cases, they only account for a few thousandths of 1% by weight. This makes them trace elements, not minor elements. Also worth noting is that the graph released in the Chinese Academy of Sciences article only covers the spectral data for Sol 1, Chang'e 3's first lunar day, while the graph broadcasted on CCTV News shows the spectral data for both Sol 1 and Sol 2. Although the resolution is a little fuzzy, you can clearly see that the spectral lines for both Sol 1 and Sol 2 overlap each other remarkably well, indicating that the soil is similar at different areas, and not the result of accidentally sampling an odd rock on Sol 1. It also indicates that the spectrometer is working perfectly fine. In summary, the Chang'e 3 soil matches well with the potassium and iron contents of the Apollo rocks, but everything else was either ridiculously too high or ridiculously too low when compared. And of course, such wacky proportions of these elements would yield mineralogy different to that of the Apollo rocks and their terrestrial and HED counterparts. The ABC report that the Smart 1 uncovered minerals different to those found in the Apollo rocks seems to be becoming more vindicated by the minute.
By punching a 10-metre hole in the Moon's surface, the probe has uncovered minerals different to the rocks gathered on the surface during moonwalks. The key is the chemical signatures in the dust and debris thrown up by the collision.
And also the radiation in the infrared can tell us the temperature, which tells us how much energy was released and what the material must be made of.
Today's collision could also unlock the secrets of the moon's origins.
So each theory of moon's formation has a prediction for what the moon should be made out of, and by looking at what the moon is actually made of, we can eliminate some theories and reinforce others.
It's hoped results will be available within a year. Michael Lockerbie, ABC News, Hobart.
That was 8 years ago, and as far as I can tell, neither the results of the impact observation nor the results of any re-evaluation of the moon's origin theory based on the impact data has been published. Now, after 8 years of Smart 1's different minerals being swept under the rug, China announces that their Jade Rabbit rover has found that the chemical composition of the lunar soil is also different to the Apollo rocks. And before anyone wants to peddle the claim that finding different rocks at unsampled locations on the moon is to be expected, let me remind you that that's not what you said before the Smart 1 impact. Also, it goes without saying that if the Chang'e 3 results are accurate, the implications go far beyond determining whether Apollo was real or not. Because it also indicates that the moon might not have originated from a Mars-sized HED planet colliding with the Earth, as geologists studying the Apollo samples have concluded to try and explain away the alleged lack of water in the Apollo samples and their composition similarities between terrestrial mafic igneous rocks and HED meteorites. Not only that, but it would also help completely reshape our understanding of how rocks form, because to the best of my knowledge, there is no such thing as a calcium-based igneous rock. There are some sedimentary rocks here on Earth like limestone that can contain up to 45 to 50% calcium oxide. But of course, being sedimentary rocks, they are the products of alteration by significant exposure to water and weathering processes that don't happen on the moon. And the only places on the moon where you'll find huge amounts of water is in the poles. Even if you could get sedimentary rocks on the moon, sedimentary rocks definitely don't contain titanium in comparable proportions to their calcium content. You'd think that planetary scientists would be all over the spectral data with gusto. So far, though, this chart has barely raised an eyebrow, let alone a detailed analysis. The only question that remains is, where do we go from here? In the past year, I have proven that the frame rate of the Apollo 11 EVA telecast was 24 frames per second, not 10 frames per second as NASA claimed. Meaning, it had to have been shot with a camera that reportedly was not in NASA's possession when they were supposedly on the moon. I also showed that the American flags would have been destroyed by radiation and micrometeoroids decades ago, as was the case with the Mir flag. Therefore, any photos of LRO showing a flag casting a shadow, or rather, a smudge of pixels that we are supposed to believe is a flag casting a shadow, is a photo manipulation. Which begs the question, why would they need to photo manipulate post-Apollo photography if the missions were real? Now, after nearly a decade of waiting, we finally have a ground-based survey to correlate with the Smart 1 impact. As far as I'm concerned, there is absolutely no question in my mind that Apollo was a hoax. And quite frankly, evidence-wise, I can't imagine topping that. I could easily produce 10 more videos discussing the inconsistencies between the Chang'e 3 photos and the Apollo photos, and believe it or not, there are a few other issues that I haven't addressed yet. But after this video, it would ultimately be anticlimactic. The only thing that could possibly top the findings by Chang'e 3 would be resolving the Apollo sites with a huge ground-based telescope and finding nothing, or a private organization with absolutely no ties to NASA sending an unmanned rover to the Apollo sites and finding nothing, or a future crew dying from space radiation trying to get there. Let us hope that we never have to cite option 3. Now, if you'll excuse me, I have to focus on solving the radiation problem and getting men on the moon for real.